One more video for class number 15. Here is an example from Cengel's Thermodynamics book. This is example 510, cooling of refrigerant 134 by water. And we have refrigerant 134. It's cooled with water and condenser. The refrigerant enters the condenser with a mass flow of 6 kilograms per minute at 1 megapascal, 70 degrees Celsius, and it leaves at 35 degrees Celsius. I'm assuming that the pressure is pretty close to being the same in and out. The cooling water enters at 300 kilopascals and 15 degrees Celsius and leaves at 25 degrees Celsius. It too probably has about the same pressure. Neglecting any pressure drops, well, that's what I just guessed. Determine the mass flow rate of the cooling water required and the heat transfer rate from the refrigerant to the water. Basic heat exchanger problem. I already gave you a heat exchanger problem for the homework that's due right now, so it seems a little mean to be doing that, but more is better. Good practice. So I'm going to call this M.R. Yeah, sure. We have 6 kilograms per minute. Quick math, that's 0.1 kilograms per second. The pressure 3. I guess I decided to go with 3 first. Okay, so here's the refrigerant coming in. That was 3, was 1,000 kilopascals, and the temperature was 70. So I think at table B.5.2, we found that the H3 was at 452.34. Now, what was interesting is that Cengel's tables do not match Borgnacki's. They have different, completely different here. I thought that was very interesting. You probably don't, but I do. All right, so we could see that at that same. All right, so I guess, is it true? Yeah, I guess we're going to go ahead and assume that this thing, it condenses. It says it's a condenser. So we're going to say that it becomes a fluid completely. So if I go to table B.5.1 for this right here, at the temperature of 35 degrees Celsius, I want to know what the pressure is right here. I decided to go 8. I didn't write it down, so maybe we're going to take a little detour here. And we're going to say that H4 was equal to the HF at that 249.10. But you know, the pressure does play a role here, so in the saturation. But it just says that the refrigerant enters there and it leaves at 30 degrees Celsius. Interesting. So let's see. No, don't go there. I'm going to go up to here. Where'd you go? Boom. So we got this. We have which one? This is. Oh, here's the refrigerant 134. Okay. And sure enough. Okay. So this is actually the spot we want to go to, and we were going to go do 30. Right? Is that correct? We're no 35. Excuse me. Don't give me your 30. Okay, so the saturation pressure is it's okay. It's in the ballpark. It's kind of like it would be probably somewhere in between these two, right? Because it should be like right around 1,000 megapascals, which is be in between here. So maybe that's what they're doing. Here's the enthalpy. I decided to write down this enthalpy right here. So this is going to be an estimation. We just estimated that it was this fluid. I can explain to you why that's the case. The way these work in a very simplistic when it's a condenser, right? So here's an explanation for a condenser. Is the outlet, or you could think, I don't know how to draw it right here. Let's see. The outlet has a valve. It doesn't really have a valve like that, but it's usually in part of the thing. and it's got like a little lever on it, and it'll let me see here. I'm gonna go the other way. There you go. And it's got a float, right? So just sort of like a toilet, kind of. And if this goes down, it shuts off the valve. But if it goes up, it opens the valve, right? And so what it does is by doing this, it always maintains a mixture of liquid and gas in a condensed state. So the only thing that will come out is the condensed state of this thing. So that's the reason why, and there's lots and lots of contraptions of various sorts, but they all kind of have sort of the same idea. And sometimes this could be considered a trap, right? It's sometimes called a trap, and it'll stop. It's trapping the gas from just blowing right out through this right here, and then no heat exchange is going to take place. But this little level control right there always kind of make sure that there's always a combination of liquid and gas in there. So a lot of times there'll be a steam trap, and if you were to have like using live steam in a radiator, you would hear all kinds of noises and stuff going on because of the change in phase for things. And if your trap breaks, that steam's just going to go right through there and won't actually work very well. But let's go back to this right here. Sorry. So they got kind of close right here. The PSAT was within the range of reasonableness, I suppose, but it's not exact right. Continuing on, let's go to table for water. Let's go to table B.1.1, and we can just look up at these temperatures. The fluid enthalpy, 62.98 kilojoules per kilogram, and then at T equals 25 degrees Celsius, we have HF is equal to 104.87 kilojoules per kilogram. So here you go. Here's the I like to do the summation. Okay, the summation. Summation of M dot N H N minus summation M dot exiting H exiting. We'll say it's insulated, so nothing's escaping. No work is being done for here, so all we're left with is the mass of the flow of the refrigerant times H3 is coming in, plus the mass of the water. Where'd I go? Water? I just want water this time. Didn't give it WTI. And that's 1 coming in, so H1, which should have been, I should have labeled these right here, right? This was equal to H1. I think this was H2. It's equal to that. Minus M dot R H4 minus M dot W times H2. So I can rearrange these. H3 minus H4 is going to be equal to M dot water H2 minus H1. We know this of 0.1 kilograms per second. We had our refrigerant that was dropping from H3 to H4. So H3 we said was 452.34, and H4 was right there, right? So we had that one and that one. So we had 249.10 It was equal to my m dot, which I was trying to find, of water. And we could do, by the way, could do CP delta T for this. That's totally, it's, you know, we're only changing from 20, from 15 degrees to 25 degrees, but we went ahead and looked up the enthalpy here. That's totally fine. Either way we could have done it because it's right there in the range. We could find what our m dot water was going to be 0.4852. And these are going to be kilograms per second. All right, so they asked us, though, what the heat rate was. We could do it either way. This is going to be the heat rate, and this is going to be the heat rate. We could even just go up to here on this equation right here and only look at one side of the heat exchanger, although it would be kind of tough to draw that. Like, you know, like what we could do is we could, you know, draw the pipe right here of the pipe coming in. And then we could go, right, like make the control surface around there, and then say, oh, here's our Q right here, crossing the thing, and then here is our M in and M out. Right. So in that case, what we'd say is Q, or don't equals Q minus W plus summation M dot in minus m dot exiting. But now, you know, and this one I guess would be for the refrigerant. So we would say, well, this goes away right here, but we would say Q, boom, and you go minus m refrigerant times H 3, no, not minus, right there, plus, minus m dot refrigerant, and that's H 4, right? And our Q dot is going to be equal to MR H4 minus H3. I think that's going to be right. Should we go on to the other side, right? And so because it's leaving, this heat's leaving, we're going to get a negative number. So you get 0.1 times 450. Whoop. 249.1 minus 452.34. And you should get a Q dot between 3 and 4. 3 and 4. And you end up with a minus 20.32 kilowatts. And as I mentioned, we could do the same thing, but backwards, I guess. But no, I'm trying to be creative here. And so we had water coming in here and water coming out there, and then we had heat transfer in, right? And that would be between 1 and 2. Here's our mass dot in and H in, and here's be mass dot H in and mass dot H out. But we could also, because it's just water and it's only changing about 10 degrees or 10 degrees, we could use the specific heat for the water instead and come up with the same values. And so let's just go ahead and do that with the results that we got from up here. We could say Q from 1 to 2 is going to be m dot water CP T2 minus T1. So the 0.4852, the specific heat of water, I think is 4.18. We could find that in the tables. I think we found it in the tables. Have we looked before? I think we have. If we go to A, I think it's A, there it is right there, A4. you find the specific heat of water is right here, 4.18 kilojoules per kilogram degree Kelvin, right? And it's only 10 degrees difference. So hopefully, I'm going to look like an ass if that doesn't work out. 0.4852, 4.18 times 10 times, boom, we get ourselves equal to 20.28. Damn close. Just a little tiny bit off. So anyway, there's a great video. Sure, it was wonderful. You loved it. It was life-changing. Sure. I'll see you in class 16.